All right, you want to get something to take notes with before you proceed any further with this lecture. Okay, so we have our compound statement here on the screen, and we don't know the truth value of this compound statement. We don't know whether it's true or false, and we don't know whether it's true or false because we don't know the truth values of any of the simple propositions that make up the compound statement. In fact, we don't even know under what conditions this statement would be true or false. And that's what we're going to explore in this lecture here. We're going to figure out how to create a tool that will reveal to us under what conditions this statement is true and under what conditions this statement is false. Okay, so meet your new best friend, L equals 2 to the n. No, we're not going to start doing math, but we are going to use this formula to help us create our tool that allows us to evaluate statements and ultimately to evaluate arguments for validity. All right, so what does L equals 2 to the nth power mean, you ask? That's a good question. Okay, the n in L equals 2 to the n represents the number of unique propositions that comprise the compound proposition that we're looking at, okay? So this n right here, the number we're going to plug in there corresponds to the number of propositions that make up our compound proposition. So what's that number? Did you say 4? No, 3, right? The number of simple propositions that make up our compound propositions are 3. It's T, H, and L. H appears twice, but it's not a unique proposition each time it appears. It's just a repetition of the original proposition. Okay, so now what we do is we plug in the number of unique propositions, 3, into our n position, and that gets us L equals 2 to the third power. And then we calculate that. What is 2 to the third power? Did you say 6? No, it's 8. Okay, so 2 to the third equals 8. Fine, you're thinking to yourself, what does this mean? What do I do with this 8? Well, that 8 represents the number of lines that I'm going to need to draw. So I'm going to take my statement, and I'm just going to draw 8 lines underneath this statement. Okay? And each one of these lines represents a unique moment in time. So maybe line 1 is next Tuesday and the way that reality is structured on that day. And maybe line 4 is a month from now and how reality is structured this way. And what I'm going to do is I'm going to use my L equals 2 to the n to figure out all the possible combinations of true-false values for this compound proposition. How am I going to do this? Okay, well, after I've done step 1, which is to determine how many lines I need to draw underneath my statement, I'm going to look really carefully at this guy right here, number 8. And I'm going to take that number, whatever the number was from my original calculation of L equals 2 to the n, and I'm going to divide it by 2. And that's going to give me a number that indicates how many T's followed by how many F's I need to draw underneath the very first letter in my compound proposition. So I'm always going to start on the furthest left-hand side of my what's called a truth table. I'm always going to start with this column underneath the first letter here, and I'm going to draw half of the lines with T's, which stands for true, and half of the lines with F, which stands for false, okay? Then what am I going to do? Well, I'm going to come back and I'm going to look at this number, the number I got the second time I used L equals 2 to the n, and I'm going to divide it by 2, okay? And what that's telling me is, okay, move from the first column you filled in true-false values for to the next simple proposition and draw 2 T's, followed by 2 F's, followed by 2 T's, followed by 2 F's. Now, one thing I want to make sure I do, this is super important. I want to make sure that on every line H appears, on every line where I have to fill in a truth value for H, that the truth values match, right? Because if each one of these lines is a particular moment in time, and any given statement can be either true or false and never both, then when it's true here, it has to be true here as well. And when it's false on lines 3 and 4, it has to be false on lines 3 and 4 here as well, and so on and so forth. Okay, so now I can move to the next step, which is to look back at this number I got the second time I calculated, or the third time I calculated L equals 2 to the n. Guess what I'm going to do to it? Did you say divide by 2? Yeah. Okay, so I'm going to divide that by 2. That tells me, look, go to the next letter to the right, and I want you to put 1 T, followed by 1 F, followed by 1 T, and so on and so forth until you get all the way down to the bottom of your truth table. Okay, so now what I've done is this. I have revealed all possible combinations of true and false values for the propositions that make, the simple propositions that make up this compound proposition. Okay, so all the possible truth values are now revealed in this truth table, and I can take the next step, which is to start working inside parentheses to calculate other values of the operators based on what I know about the rules for operators. So I see I have two conditional statements here in parentheses, and I have this handy guide to conditionals. It's my own truth table for conditionals. And I know a couple of things. One thing I know is that anytime the right-hand side of a horseshoe is true, like it is on lines 1 and 3, the horseshoe is true. So I can go ahead and look at all of those areas where the right side of the horseshoe is true, and I can mark that horseshoe as true. The other thing I know about horseshoes is that anytime the left side of a horseshoe is false, the horseshoe is true. So now I can go in and fill in all of those other truth values for F. Okay, now I've got all the truth values for my two propositions on each side of the dot, and now I can calculate for dot. I can figure out what the truth value is of dot using the rule of conditionals, okay? That rule, the rule of dot is going to be determined by the values underneath this horseshoe combined with the values underneath this horseshoe, and I know that the only time a dot is true is reflected here by line 1. It's when what appears on each side of the dot is true. So on any line where these two horseshoes are true, the dot's going to be true. And on any line where one or both of the horseshoes is false, the whole horseshoe or the whole dot is going to be false. Okay, so now look what I've done. I've created a truth table using L equals 2 to the n that reveals not only all of the truth value combinations for the simple propositions that make up our compound proposition, we've also been able to reveal all of the truth values of the operators of this compound proposition. And now what I can do is I can look at this truth table and I can look to see under what conditions this compound proposition is true. Okay, so like on line 1, well, if everything being said is true, then obviously the entire statement is true. But look at some of these other lines. It's possible that the simple propositions are all false, and yet the dot is still true. Okay, so there's lots of interesting stuff going on here that's now revealed in this truth table, and I can identify under what conditions this statement is true and under what conditions this statement is false. And that's what we're going to start working on, our truth tables. This is a tool that represents every possible truth value combination of the component parts of compound propositions, and we can use these truth tables to help us evaluate statements, to understand how they function, to help us compare statements, to see how they relate to one another, and ultimately how to evaluate arguments for validity.